Welcome back. Today we'll look at the graphs of polynomial functions. Before we start graphing, let's review some vocabulary. So remember, a polynomial function or equation in standard form is always writing the terms in degree order. So we always start with the highest degree first and then write the terms in descending order. When we consider the types of polynomials, we describe them by the number of terms. So if something has one term, it's called a monomial. You could have something like 5x, 12, which is a constant, negative 3x squared, y. So all of those are monomials. Binomials are two terms, polynomials with two terms, and they're always either added or subtracted. So you can see two monomials there, 2x squared and 7x, but it's 2x squared minus 7x, so we have two terms in there. A polynomial with three terms is called trinomial, like a tricycle. So if we have three terms, we have 8x to the fifth plus x plus 1. Those are three terms, so it's a trinomial. Any polynomial with more than three terms is just called a polynomial. Now, when we consider polynomials, we want to look at two important things. The first is the degree. The degree of the polynomial is going to be the highest exponent. So when we look at the degree of each term, the highest degree will be, the greatest degree will be the degree of the polynomial. The leading coefficient is that number, that value that it's not going to be 0. It could be 1. It could be any number, but it will be in front of the variable with the greatest exponent or the highest power of x. Okay, depending on what your variables are. Maybe t, but whatever the greatest power is, that number in front will be the leading coefficient. Now let's classify this polynomial. Well, you can see right away that this has three terms. So we know this is going to be a trinomial. Now I want to remind everybody that we want to make sure whenever we're looking at polynomials to write them in standard form. So to write them in standard form, remember we have to have it in descending order by degree. So 2x cubed is first. That's the highest power of x. And then we'll write minus 4x because that's just x to the 1. And then our constant will be last because really that's x to the 0. So we could tell that we're going by degree in descending order. So 3, 1, 0. So it's in descending degree. Okay, so now let's consider the degree of each term. And we kind of alluded to that. But the degree of the term 2x cubed, this monomial, is going to be 3. That's the highest exponent. That's the exponent of x. The degree of the term negative 4x would be just 1. Because even though we don't write that 1 in simplest form, we do know that that's going to have an exponent of 1. And then the degree of any constant, like 9 or 10, whatever, this number is 9, it actually is 9x to the 0. So the degree is 0. So this describes what's the degree of each term. Now when we say, well, what's the degree of the whole polynomial? We just look at these numbers and we say, what's the highest? What's the greatest? And so we say, it's going to have a degree of 3. And we know that something with a degree of 3 is a cubic function. Not a quadratic. Quadratic is 2. So this is a cubic. And just as a refresher, I'm just going to write these over here. So if we have a degree of 0, and this is the polynomial degree, well, that's called a constant. When something has a degree, when the polynomial has a degree of 1, that's going to be a linear function because it's just x plus 2 or x, whatever the number is. When it's a degree of 2, well, that's a quadratic. And if it's a degree of 3, that's going to be a cubic. And we're going to go higher with these polynomials, but those are the important ones. Now, looking at the degree, we're really going to focus on this 2x cubed. That's the highest degree monomial in this polynomial. So it actually, is going to trump any value or any other degree in this expression. So when we say what's the leading coefficient, we only look at that term. And the number in front of x cubed is 2. So this 2 right in front, that's our leading coefficient. And that's going to be really important. It's positive 2. And we want to make sure we know that. That's going to be positive 2. And this trinomial has a degree of 3. Okay, now when we consider looking at polynomials, we want to figure out what they look like with the graphs. So what we're going to do is actually look at some of these polynomials and consider the degree and the leading coefficient. So I'm going to zoom in here so we can see. So right here, all of these have a degree that is odd. 1, 3, 5. We have a linear, right? So that exponent is just 1. We have a cubic right here that has a degree of 3. And we have, it's a quintic. So we have a polynomial with a 5th degree. So when we look at all of these, well, you can see that all of these actually end up going as we get higher with these x values. So we start with 2, 0, 1, 2, 3, 4, 5. As we continue on into positive infinity, all of these functions are going up higher, right? So that's going to the positive, it's going up positive. So as x is approaching positive infinity, these functions are also approaching positive infinity. So when we talk about end behavior, we're saying, how is that ending? What's the ending of the story? What's the ending of this function? We're saying as x approaches positive infinity, y is going to approach positive infinity. Now, if we look at the left side, and it's kind of tricky because we're saying ending, but it's really starting. So it's ending. We're saying on the left side, if I stop this graph, how would this function end going towards negative infinity? So if I keep going over here, and I say, oh, let's start with 0, -1, -2, -3, -4, -5. We keep going into negative infinity. So this is going to be the x value, right? So the x value is approaching negative infinity. It keeps going further into the negatives. Well, we can see all of these functions are going down. They're all going lower and lower and lower. So that means the y value is also going to go down. It's going to keep going down to negative infinity. So that's what we mean when we talk about end behavior. We're saying, well, if x is approaching positive infinity, the y is approaching positive infinity. As x continues to go positively, y is going in the positive direction. And as x approaches negative infinity, y is going down towards negative infinity. So this is when we have an odd degree. Remember we said all of these were odd degrees. And the leading coefficient is positive. So you can see right here, the leading coefficient here for f of x is 1, for g of x is 0.5, and for h of x it's 2. And that makes sense, right? So if it's positive, it has a positive slope, it's going to be increasing. So it's going up. Versus when it's an odd degree going down, or negative when it's decreasing, we can see the opposite. So over here, as x approaches positive infinity, as we go further to the right, you can see that all of these functions are going down to negative infinity. They're going down, down, down as we keep going to the right. So as x approaches positive infinity, f of x is going down to negative infinity. Right? That's going to be decreasing. But if we go over to the left side, to the end behavior, and we say, well, what happens when x approaches negative infinity? Well, all these arrows are pointing up. So as x approaches negative infinity, the function is going to go to positive infinity. It's going up. And that's going to be a decreasing function, generally, right? So in general, it's decreasing or increasing. And so this is only when the functions are odd, right? We're looking at these polynomials with an odd degree, and positive, which is increasing, and negative, which is decreasing. Now let's look at polynomials that have an even degree. So if something has an even degree, we're looking at, again, the highest degree in this polynomial, and you can see they're all even numbers. We have an x squared, we have a quadratic, we have a quartic, right? We have something to the fourth, we have something to the sixth. They're all even. And the leading coefficients are all positive. You can see a 1 right here. They're all going to be positive. 0.9, 2. And so when we look at these functions, we're saying, okay, let's look at this function as x approaches positive infinity. What happens to the functions as we go to the right? Well, as we go to the right, all these arrows are going up. So f of x, or you could say y, is going to positive infinity. And then when we go to the left side, we say, well, what happens when you have negative values? You go -2 for x, -4, -6, and as x approaches negative infinity, what happens as you go to the left? Well, they're all still going up. So the end behavior is going to be f of x approaches positive infinity all, for both times, for when x approaches negative infinity and when x approaches positive infinity. So we have both of those, really those arms of the function, if you want to say they're arms, they're going to be opening up because it's a positive leading coefficient. Well, the last scenario is when we have an even degree and a negative. And so when you have a negative coefficient, so you can see you have a -1 right there, still degree that's 2, you have a -0.9, it's still an even degree, and a -2, that's a negative, but still an even degree. We're looking at exponents. Well, look at these functions as you approach positive infinity, as x approaches positive infinity, as we go to the right, all of these arrows are pointing down. The y, or the f of x, is going towards negative infinity. And then if we go to the left and we say, well, what happens as x approaches negative infinity? As we go -4, -6, -10. As we keep going to the left, all of these arrows are pointing downward. So it's going to be negative infinity as well. So we also call them the arms of the function. And so we can tell when it's positive, well, those arms are opening up. When it's negative and even, those arms are opening down. And so just to kind of give a little visual, when it's odd and it's positive, the left arm is down, the right arm is up, right? And then if we say, well, let's look at the odd degree with negative leading coefficients, those are decreasing. So the left arm is up, the right arm is down. So those are all the 4 different scenarios when we consider the leading coefficient. We look at the degree, it's either going to be even or odd, and then we look at the leading coefficient, and it will be either positive, like +2, or negative, like -2. Well, now that we understand end behavior, let's graph the polynomial function. So right here, you could tell that this function right here will be a trinomial, and looking at that leading coefficient and that leading term, we know that this is going to be, I'll put a trinomial. We know that it's going to have a degree of 4, and that's even, right? 4 is an even number, and the leading coefficient is negative. So with a negative leading coefficient and an even degree, we can anticipate what the end behavior will be. So remember, if it's even, the arms are going together, and it's negative, so both the left and the right side will be pointing down. So as x approaches negative infinity, y will be approaching negative infinity. As x approaches positive infinity, f of x will also be approaching negative infinity. Now, whenever we want to graph a function, we always want to make a table. And so when we have this table, we can actually see what's happening to the function. It has a little story here. So the values are going up and then the values are going down. So I'm going from least to greatest. We're starting from left to right. And I'm going to graph this below. But we want to see what's happening with the y's. Well, we're starting with 11.5 and then we go up to 6. So that's why it's increasing. But then as soon as we go to 6, we end up going back down to 4.5 and then to 2. So that means that it's decreasing in that interval. And since 6 was where it started going up and then started going down, that's going to be a turning point. And if we could think of something that's going up and then going down, we know that that's going to be a maximum or relative max, because this function is definitely going to keep changing, so it's a relative max. And so this point, -2, 6, is a relative max. As we go down to 0, 2, you can see that it starts to go back up. So 2, or 0, 2, which is x equals 0, is going to be another turning point. So this is 0, x, these are the x values, and then we know that that's 0, 2. And then as we go further down the table, we could see that 6 ends up being another turn, or it turns again at 6. So that's 2, 6. So you can see right here, if this is y equals 6 right here, we know that 2, 6 is on the graph, and we know that -2, 6 is also on the graph. So if we're going to graph this, we could sketch the points. So we could see -2, 6 right here. We could see 2, 6 and all these other points, and that's so we know that around here there's going to be a relative max. It changes. And we know at 0, 2, which is right here, that was another turning point. So the turning point is where the function is changing from increasing to decreasing, or vice versa. So we call those turning points because that's what's happening. The function is turning. And we actually have two types of turning points. We could have maximums, right? So if something is increasing and then decreasing, and then we could have minimums. So this would be a max, and this would be a min, or minimum. And so this means that we're increasing here, and then we slow down, and then we decrease, and then a minimum would be decreasing, hit the minimum, and then start increasing again. So when we look at turning points, we want to make sure we're looking at those relative maximums and relative mins. For example 4, we're going to graph or sketch this graph based on a verbal description. So what's going to happen is it's telling us that the function is going to be positive from -infinity to -4, and then 1 to 4. And what's really important is that, remember, these are all the values for the x. So we want to make sure that we put them on the graph. And then right here we have, it's going to be negative from -4 to -1 and 4 to infinity. And then the function is going to be increasing from these two, from -infinity to -2.67 and 2 to infinity. And the function will be decreasing from -2.67 to 2. So remember, when something is positive, it's going to be above the x-axis. So I'm just putting these points here. And so we know that the function is going to be above the x-axis. And I'll put this in green right here. So it's going to be above right here. It's going to be above between -1 and 4. And then we know it's going to be negative, I should say, between -4 and 1 and 4 to infinity. So when we try to figure out those x-intercepts, that's what we first need to make sure we focus on. These are the x-intercepts, and we know that the functions are going to change. If this is negative, it has to go through this x-intercept, or I could say 0. And we know it's going to go through this function here. So we know in general it's going to go up and down, and then this function is going to end going up. This function will end going down. Now we want to figure out some of these turning points. So the turning points are going to be in between. So we have -2.67. So we have -2.67 right here. I'm going to put this right here. This is -2.67 and some value for y. And then we have another turning point at 2. So I'll put 2 here so we can see another y. So we know that these are going to be turning points. Those are going to be the max. This is the maximum here, and this would be the minimum. So it says the relative minimum at x equals -2.7 and a relative maximum at x equals 2. And we get to double check, we can also look at those slopes. So remember, we had something that was decreasing. We said, okay, let's make sure it's decreasing from -infinity to -2.7. Yes. And it's going to be decreasing from 2 to -infinity, or to positivity. Yes. And then it will be increasing. Was it a different color here? It's going to be increasing from -2.7 to 2. So we can kind of see this function right here. It's going to be definitely odd. It's definitely going to have a leading coefficient that's negative. So we can see the end behavior here. We know that it's going to have a left hand up, right arm down. And then if we sketch it, we could plug those points in, and you can see in general, it's going to have that pattern. We said it's going to have a minimum here at that -2.67 and a maximum at 2. So we just have to connect those points, and we can sketch them with a graph. It does help to have the graph paper. Now let's consider an application. In science class, Abby mixes an amount of baking soda with different amounts of vinegar, which is capped by a balloon. She records the amount of time it takes for the gases produced by the reaction to inflate the balloon. And she writes that with the data, she's able to make an equation. So for X number of quarter cups of vinegar, it will take this amount of seconds to inflate the balloon. So again, we can see that X is the number of quarter cups, and then T of X is the time in seconds. For this first problem, it asks, how long will it take? So we're looking for the time to inflate a balloon with 5 quarter cups of vinegar. So that means we're going to substitute in 5 wherever we see X in this equation. So T of 5 would equal 0.125 cubed plus 5 squared minus 3.38 times 5 plus 13.16. Well, we know 5 cubed is 125, and if we multiply that with negative 0.12, that'll be negative 15. This is 25. This will be negative 16.9. And when we add all of these numbers together, we get 6.26 seconds. So it'll take about 6.26 seconds for that balloon to inflate. Now let's look at the graph and figure out what these x and y intercepts mean. So remember, this is the y-axis, so we can see the y-intercept is up here. So the y-intercept is saying that if we don't have any vinegar, because remember x is the vinegar, so with no vinegar, it will take 13.16 seconds to inflate the balloon. Well, that doesn't make sense. It doesn't, so unless something else is happening, no, the balloon wouldn't be inflated, right? So there has to be something, some sort of, maybe somebody's doing it themselves, like blowing the balloon up, or there's a chemical reaction. But if no vinegar, that means there's no reaction, so it's saying that it will inflate 13.16 seconds. If we look at the x-intercept, it's saying if we have 6.8, well, about 6.6, but 6.585 cups of vinegar. So I'll put this here, 6.585 quarter cups of vinegar. The balloon will inflate in 0 seconds. Well, that doesn't make sense either, because that's like that'd be faster than lightning. So, so if it was going to inflate in 0 seconds, something instantaneous would happen, right? So that doesn't make sense. So even though we have these values and she was able to find this equation, make this model with the data, we really need to make sure we restrict the domain and range. So because they don't make sense, so I'll say this doesn't make sense, we're going to restrict the domain and range. And if we restrict the domain to really just values between 0 and 6.58, so not including them. So this is the domain, and we're just saying we're just looking at these values and not including the x and the y intercepts. Then we can we won't have these really weird scenarios over here. Okay, so as a summary for this section, remember we were looking at polynomial equations and we're trying to describe polynomial equations by the degree, by the leading coefficient, and the number of terms. We're looking at the graphs and we're looking at tables and saying, well, when are these functions turning? If they're turning and they're becoming from decreasing to increasing, this is actually opposite here. When it's going down and then up, it's going to be a minimum. When it's going up and then down, that's going to be a maximum. Now, something that's really different for this section and very important is looking at the end behavior. So when we look at the end behavior, we're trying to decide first, is it odd or is it even? If it's even and positive, it's going up. Both the left and the right arm are opening up. If it's odd and positive, it's almost like an increasing function. So the left arm is down, the right arm is up. When it's odd and negative, it will be decreasing. And then if it's even and negative, both the left and the right arm are going down. I hope this lesson was helpful, and I'll see you all in class.